Alright guys, we're down to chapter 2.1, section 3.1 outline. Number 1 says a set is any collection of objects or ideas that can be listed or described. That could be 1, 2, 3, 4. It could be A, B, C, D. It could be red, yellow, green. I mean, it could be anything that could be grouped together. An element inside a group is each individual object in a set. So if we look at some of these sets over here, a set is all the group of characters. An element, which is written as that symbol, it's each individual item in that set. So an element of, let's say that this is set A, an element of set A would be 1. An element of let's see, if this is set B, an element in set B would be D. And if this is C, an element of set C would be green. An empty set is a set that has no elements in it, which is, so it's a set that contains no elements. A finite set is a set that has a limited number of elements. Which could be like, let's say, the number of people in a classroom, or the amount of girls in a classroom. It'd be a finite set, only a certain amount can be in that class. An infinite set would be all positive numbers, like the number would go on and on and on and on, like there's no limit to it. So it'd be a set with an unlimited number of elements. So like you would say, like an infinite set would kind of look like 1, 2, 3, 4, 5, and then it would go ellipses, and then end like this. So it means it just goes on and on and on. There's no stopping it. All right. Number 2, it says one-to-one correspondence. Set A and B have one-to-one correspondence if and only if says each element of A is paired with exactly one element of B. And each element of B is paired with exactly one element of A. So an example would be, let's say we have T and V sets. So we have a set of blue, red, and yellow. And we're comparing them to set V, which is A, B, and C. They are one-to-one because each one has a corresponding item. So they each have 3 elements in each, so they can be compared evenly. Okay, so now we got equal and equivalent sets. Okay, it says sets A and B are equal sets, symbolized by A to B, and only if each element of A is also an element of B, and each element of B is also an element of A. So that would mean like they, okay, so let's say if you have set A and set B. Set A would have 1, 2, 3, and 4. And B would have 1, 2, 3, and 4. That means A is equal to B because they each have the same number of elements, and in each set, the elements are the same. They're both identical. So now if we go to the next one, it says set A and B are equivalent sets, symbolized by, I don't remember what this is called, but it's like a, it says if and only if there is a 1-to-1 correspondence between A and B. So that means like if we have the A and the B, A would be 1, 2, 3, and B might be 4, 5, and 6. They are equivalent because they have the same amount of elements, but they're not equal because those elements are not the same. So it's only equivalent, but it's not equal. So, okay, so number 4, subsets and proper subset. What is a subset? A subset says for all sets A and B, A is a subset of B, symbolized as A, B, if and only if each element of A is also an element of B. So that is saying like, say we have A, a set A has 1, 2, 3, and 4. The subset of A, if B is a subset of A, it would be like it have the same elements in it. Like it's a part of A. Now, proper subset, it says for all sets A and B, for all sets A and B, A is a proper subset of B. If and only if and only if A is a subset of B, of B, and there is at least one element that is not an element of B, that is not an element of A. Okay, so what all that means is say you have A and B sets, and A has 1, 2, 3, 4, 5, and 6. B would have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So A is a subset of B because all the characters in A are actually in B as well. But to make it a proper subset, B has to have more elements than A that are not included in A. So that's the difference between like a regular subset. It has to have the same, but a proper the B has to have more than actually the A. Okay, how is it symbolized? So it would be like the A is a proper subset of B. A set is a subset of itself. And because that means like a subset would be any number of the elements in a set. But it could be all of them, it could be none of them, it could be one of them, two of them, depending on how many are in the set. So that means it's a set is a subset of itself because it could be one of the options that makes up that set. A universal set is made up of all the possible elements that could be considered in this situation. So a universal set, what it is like, say we have set A has 1, 2, 3, and 4, and B has 2, 4, 6, and 8. The universal set of A and B would equal all of the ones that are connected to both. So we'd have 1, 2, 3, 4, 6, and 8. So you'd only list them once because A and B both have 2 and 4. You'd only list those numbers once. So it's all the numbers that are included in all the elements or all the sets that are being compared. A set that contains no elements is empty or null is denoted by either like an open bracket or like the 0 with the slash through it. Sorry, I'm writing kind of small. A complement of set A, written A with the line over it, is all elements in the universal set that are not in A. So if we go back to like this example right here, the universal of the A would be all the ones that are in B that are not in A. So it would be like, it would be 2, 6, and 8. Or no, that's not right. So all the elements in the universal that are not in A. So it would be all the ones that are not in A. So it would be 4, nope, not 4. It would be 6 and 8. Sorry. All the ones that are not in A. So it would be the 6 and 8 are not in A. So the complement of set A is written as the A, the line over it. That consists of all the elements in U that are not in U, or in A. Okay. Sorry. Venn diagrams show the relationships universal sets. A whole number is the unique characteristic embodied in each finite set and the sets equivalent to it. The number of elements in set A is expressed as n times the A. The blank of set A, the cardinality of set A. So the cardinality is the number of elements in that set. Sorry. The set of the whole numbers W is equal to 0, 1, 2, 3, and 4. The subset of whole numbers, set of natural numbers, or even numbers. Remember that the empty set is a subset of every set, and a set is always a subset of itself, not just proper subset. Sorry. So let me explain this a little bit more. So if you have a set, we're just going to stick with A. If we have a set that has, let's say, 1, 2, 3, 4, and 5, let's say, and we want to find out how many options, how many subsets would be in that set, like we would have like 1, 2, 3, 4. We could have 2, 3, 4. We could have 3 and 4. Like every number that's could be possible in there. Hold on 1 second. Okay, sorry about that. So we have all the possibilities that could make up a set is the subset. So it could be any of these combinations. It could be nothing could be possible. It could be all of the numbers could be possible in a subset of that set. It could be, let's say, 4 and 5. I mean, there's so many possibilities, and it would be so difficult to figure out how many possibilities without listing them all. But there is an equation that you can do, because if you think about it, there's two options for every element in a subset. It could either be in the set or it couldn't be in the set. So given that, you would take like 2 and you would multiply it by the number of elements in that set. So all the number n. So it could be, this one would be 1, 2, 3, 4, 5. So you do 2 times the power of 5, and that would give you, sorry, 2 to the power of 5 gives you 32. So there would be 32 sets, subsets in set A. Say we had a set that had 3 digits. It would be A, B, and C. So these will be a little easier to write out. So it would be one option, a subset would be A, B, and C. One would be A and B. One would be A and C. Sorry. The next one might be B and C. And the A and B, A and C, B and C, or just A, or just B, or just C. And then the last one would be like a 0, like nothing. Like none of them could be a part of it. So that would give us 1, 2, 3, 4, 5, 6, 7, 8 sets. So if we use that same little formula, it would be 2 times, because it could be there or not, so 2 options times the 3, the number of elements in this set, which would be the 3. So it would be 2 to the third. So that would be 2 times 4. That'd be 8. So there's 8 subsets possible for a set of 3. Hope that makes a little bit of sense for you. Okay. This one was a little tricky, but I think I've kind of figured it out. If we use a, what do you call it? A Venn diagram. So we need to go through this and find out what information are they giving us. It says 24 dogs are in a kennel. 12 of the dogs are black. 6 of the dogs have short tails. So let's say there's 24 dogs. 12 are black. 6 are have short tails. 15 dogs have long hair. Then we have some other special circumstances. It says 2 of the dogs are black, short-tailed, and do not have long hair. Then we have, so there's one dog that is black, the short tail, and long hair. And then it says 2 dogs have short tails and long hair that are not black. All the dogs in the kennel have at least one of the mentioned characteristics. How many dogs are black with long hair but do not have short tails. Okay, what I did is I drew a Venn diagram. Here, let's move this down so we can see it all. So I drew a Venn diagram and trying to get to see if I did it this way. Make it a little bit, okay, that works. Okay, so we're trying to see like what overlaps with what to see, and the question is asking how many dogs are black with long hair but do not have short tails. Okay, so that's what we're trying to answer right there. Okay, so let's start off with this. What I did is I started off with going by the special examples over here. So what I did is I say one dog is black, has short tail and long hair. So that means it has everything that's being described. So what I did is I put an X in the middle because that has all the characteristics that are possible. And then we have two dogs are black. They have short tails but do not have long hair. So that means they're common between this and this. So they are common with A and B. So I would put two X's there because that's two dogs. And then two dogs have short tails and long hair, but they're not black. So I would put the two X's here because they are shared between the long hair and the short tails. So, okay, so that's our little detailed one to kind of get us started. And we know by reading it that we have, the short tails, there's only 6 dogs with short tails. Long hair, there's 15. And in the black, there are 12 dogs. So what I did is so I know so far I've got 1, 2, 3, 4, 5 dogs that have short tails, but they also share characteristics with the other. So I know there's one dog must have no other characteristics except for having the short tail, because that would equal the 6 dogs total. So you have 1, 2, 3, 4, 5, 6. So that's the 6. So now let's go to like the long hair. The long hair has a total of 15. So what I did is I took the 3 that were already listed because they share with the other ones, and then I did 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. I did the same thing with the black. So the black so far has 3. I did 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would be 12. Yeah, 12 total. So if you count those up, right now I have 12, 15, and 6. Actually, so right now if you count all of the dogs, I have more than 24 dogs listed. So that would mean that some of the dogs that have black hair or are black and have long hair are shared. So we can, what I did is I would take one out of each side, out of each, and do it as a combined. So because right now I have 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 have black hair still. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So they still have 16 long hair, so that can't be. So what I did is I would delete one more from each side, add it to the joined. I would kind of do this until I got to where they were all even. I would take, so we have 6, 1, 2, 3, 4, 5, 6 short tails, forgot that. And then for the black, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we still have 12 black dogs. And then the long hair, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think I should have deleted one more here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so now if you count them all up, all the total dogs everywhere. So we have 6 here, 3, 1, and 2. So 6, 7, 8, 9, 10, 11, 12. There's 12 in that, plus 1, 2, 3, 4, 5, 6, 7, 8, 9 long hair, 9, 10, 11. So we have 11 and 12. 12 plus 12 plus the 12 over here would be the 24 dogs total. Sorry if this is confusing. So let's see if we got it all. So the question was, how many dogs are black with long hair that do not have short tails? So that would be the part that's in here. So that would give us the 3 dogs. All right. Let me know if this doesn't make sense. I'll help you work it out. But so that's all for the chapter 2.1. Let's go to the chapter 3, section 1. So chapter 3, section 1 is strategies and procedures for mental computation. Mental computation is a process of finding an exact answer to a computation without using pencil, paper, or calculator, or any other computational aid. So it's pretty much saying you do it in your head. Use mental computation to do the following. Well, I'll just give you the answers. Let you do it in your own head. All right, so then we got compatible numbers are a combination of numbers that might be easy to compute mentally. Oh, sorry. Example, 25 times 9 times 4 times 8. Which numbers do you choose to multiply first? Like, I would multiply like the 25 times 4 because I know that's 100. And then I would multiply the 9 times 8 because I know that's 72. So then you would take 100 times 72 would be 7,200. break apart numbers. This technique involves breaking the numbers in a computation into manageable parts to permit use of basic computative associative and distributive properties. Find an exact value of the following expressions using the break apart technique. All right, so I don't know if this is right, but this is kind of what I did. I took A, found this technique online. So it's saying like 25 times 33. So 20 and 5 and then 30 and 3. So say 25 is same as 20 and 5 and 30 is same thing as 30 and 3. So here you would take like 30 times 20 is 600 and then 30 times 5 is 150 and then 3 times 20 is 60 and 3 times 5 is 15. And then you would add up like 600 plus 150 plus 60 plus 10, and that would give you 825. So A would be 825. And then for B, did the same thing where I did like 40 and 9, and then I did just 9 over here. So 9 times 40 would be 360, and then 9 times 9 is 81. So that would be 360 plus 81. It's 441. Don't know if that's right, but that's how I did it. The number 5 says the compensation strategy involves changing the original calculation to one that is easy to do mentally. Keep track of the adjustments you make to the original calculations. Example, 19 times 11 is easier to multiply 19 times 10 and add 19 because you use one less in 19 in your modification. So 190 plus 19 equals 209. So 29 times 30, I did 30 times 30 is equal to 900, then minus 30 is 870. That's how I did it. B, consider Carrie's thinking to find 45 plus 63 plus 25 plus 17. I will first add 45 and 25. So you got the 45 and 25. Then I will add 63 to 17. I can add those answers to get the answer. Show how computative and associative properties justify Carrie's thinking. That just means, let's see, I did 45 plus 63 plus 25 plus 17 is equal to, okay, so associative, I did 45 plus 63 plus 25 plus 17. So that's associative. Because what it's saying, it doesn't matter which order that you add, it's still going to get the same amount. Computative, it's 45 plus 25 plus 63 plus 17. That's going to equal to 45 plus, oops, plus 25 plus 63 plus 17. That would equal like 70 plus 80 equals 150. Okay, number 6. Almost there. Number 6 says mental computation techniques. Counting on example 12 plus 25. So what that means is like 25 plus 10, because it's easier to add 10 than it is to add 12. So it'd be plus 10 is equal to 35, and then you'd count on to find the answer. So you would count, just keep counting to get to the plus 2. So you would do 35, 36, and then the answer is 37. So that's A and B, or sorry, that's C. And then we have D is counting back. Example 191 minus 6. So like if we have 191 minus 3 would give us, you would just kind of count backwards. So you'd have 191, 190, 189, and then 188. So our answer would be like the 188. Says counting up or back 3 digits by ones, tens, hundreds, etc. But if you do more than 3 more errors happen. So like if you're counting forward or back, it's easy to count like to 1, 2, then 3, but once you get past that third spot, then there's more chances of you like miscounting and miscalculating. So that's why that the technique is only done by 3s. Okay, so I think that is good for chapter 2.1 and then 3 on the outline. If you have any questions, just give me a call, message me, whatever's easier for you. Good luck. Thanks.